So far, we have discussed how to build models for classification. Then we also took a look at building models for regression. Both those cases were cases of supervised learning. Now we look at what can we do when we have data which is not labeled. That is, when we have a situation which you can characterize as unsupervised learning. All right, so let's take a look at that. And when we want to do that, basically what we are going to be doing is we are going to be doing clustering. So let's start with defining what is clustering. In a simple sense, clustering is really nothing but a process of grouping objects into meaningful groups. As an example, if you look at the pictures here and somebody says, well, let's group these pictures, and somebody tells you that we want to group them into two groups, what you can do is you can say, all right, there are a bunch of pictures of cars, and then there are pictures of planes. So what we can do is we can put all the pictures of cars in one group and all the pictures of planes in another group, and that will be the result of cluster. All right. Anytime you want to do grouping, essentially what you are doing is you are looking at pairwise similarities between the objects that you want to group. So in clustering, the idea of similarity is really, really important. Now, as I said, the clustering is also known as unsupervised learning. And it turns out that this idea of grouping or clustering is so useful in so many different domains that people have talked about clustering in different disciplines, and they have looked at different algorithms for clustering in different disciplines. And as a result, in different disciplines, you will come across similar set of techniques, but those techniques are given a slightly different name. So people call it unsupervised classification. Sometimes somebody will call it Q analysis, typology, numerical taxonomy, and market segmentation. Yes, please.
When you say unsupervised classification is a form of clustering, can you assume that supervised classification is what is the name for supervised classification?
What's the last point you mentioned?
What? So unsupervised classification is clustering means.
Right.
I assume that all classification are supervised.
Right. Classification basically, okay, I think sometimes people complain that they cannot hear the question. So for the people who are sitting remotely, the question that is being asked is classification by design or by name is supervised? Well, it's a question of how you build the model. If I give you an existing model and ask you to use that for classification, it doesn't matter who built that model and how that model was built. We use the term supervised classification not for actually classification, but for building the classification model. Because we are talking of supervised learning, and learning is being done to build the model. Once the model has been built, there is no supervision involved there. All right. So supervised or unsupervised, these terms are used for model building, whether we are building a model for clustering or for classification or for regression. All right. So these are the different names that people use for unsupervised learning or clustering. Now, one thing that we need to look at is that while doing the clustering, obviously you are going to be looking at the data and you're going to be doing the grouping of the data into some meaningful things. All right. But before we go into all the details, let's look at these 4 pictures that you see here. All right. These are the pictures of distributions of points in a 2-dimensional space. All right. Let's think about the average or mean vector for these collections of points in each quadrant. So let's take the first quadrant and try to figure out where is the center of those points. All right. Let's do the same thing for the second, third, and fourth quadrant. And if you do a little bit of thinking or just look at the pictures, you will find that the center for all these 4 sets of points are sitting at the same location. If you were to do the variance, again, you will find that the value of the variance for all the 4 situations is identical. That means these 4 data sets have identical first order and second order statistics. The first order is the mean, second order is the variance. All right. So basically you have 4 different distributions. But if you were looking at distributions only in terms of their first and second order statistical properties, you will say that they are identical. But when you look at them, you can see that the first quadrant has 1 cluster, which is a large cluster. Second quadrant, you can say, consists of 4 groups of points. Similarly, the 1 quadrant on the left at the bottom has again a half spherical cluster, but it's a single cluster. On the right hand side, you have 2 clusters or 2 groups of points. All right. So basically what clustering is telling you, different from mean and variance, etc., is that how is the data organized in its space. All right. So that's why you want to do clustering so that you can see what are the patterns, if any, that are present in your data. Here are a couple of clustering examples. As I said, clustering has lots of applications, lots of uses. Market segmentation is something that I already mentioned right in the beginning of the semester. Okay. As somebody who is involved in selling things or marketing things, you want to basically look at your total customer base and divide them into some meaningful groups so that each group can be targeted in an appropriate way that is most suitable for that group. So that is what we call as marketing segmentation, and clustering is actually the basis to get those groups. Another example of clustering is in the domain of pictures and videos. For example, given an image, you may want to group pixels of that image into different meaningful groups, such that if you look at, for example, the picture here on the top left, you are grouping all the pixels and coloring them as yellow because those pixels define what is being worn by that person. All right. Similarly, you are grouping all the pixels that correspond to water in one particular group, and so on and so forth. So when dealing with pictures, you can apply clustering to group pixels into meaningful groups. And this process is actually called image segmentation. And in many cases, what you need to do is you need to perform image segmentation before you can figure out what all is present in the picture. What are the different objects that are present in the picture and where they are present in the picture. Another situation where one might use clustering is that you go to some kind of search engine and the search engine, and you give a query and search engine produces lots of results. Now, instead of dumping the results just as 1, 2, 3, what search engine might do is to organize the results in different clusters. And for every cluster, it might show you 1 or 2 representative examples. And that way, you'll be able to deal with the results in a much more easier fashion. You can say that that will be a much better interface for looking at the results. So some of the search engines do that, or at least they were doing it at one point or the other. And basically you were grouping stories into different meaningful groups in response to your queries that you might be giving to those search engines. This graph is just to show you the history of clustering, in the sense that the term clustering started appearing somewhere around 1940-45, and since then it has taken off, because with somewhere around that 1940-45 you started getting analog computers and some basic digital computers, so computation became a little easier and people started doing all these kinds of things. So suddenly you can see that there were a number of books, articles dealing with clustering and all. One issue that is important when you do clustering is how many clusters to form, or what should be the number of groups that you should be ending up with your data. All right. So if you look at this picture, and suppose this picture was what was presented to you in 2 dimensions. So basically we have a collection of points in 2 dimensions. And if I was to ask you, okay, how many clusters you see? All right. What will be the most common answer? How many clusters do we see here? Give me an answer. 5. All right. Okay, so you can say, all right, 5 is a decent number. All right. And looks like 5. All right. But somebody might say, well, you know, maybe it's not 5, but these 3 small clusters that we have on the top left, they could be considered as 3 separate clusters rather than putting them into 1. All right. So in that case, the number will change. All right. And same thing could be done for the cluster on the second side, on the right hand side, where you have a bunch of points being enclosed by an outer circle or so. All right. So the point is that in many cases, it is really difficult to specify how many clusters are there. And generally the number or the result that will be accepted is the result that can be supported by some hypothesis or by some domain knowledge that says, okay, yeah, this number makes sense, but this number doesn't make sense. Or looking at this result as 4 clusters or 5 clusters justifies the hypothesis that I'm proposing. All right. So typically, clustering results will be validated using some kind of domain knowledge or using some kind of hypothesis that the explorer or the scientist or you as a person have when you are doing clustering. All right. And of course, multiple clustering results are possible. It depends on how are you defining your similarity. What is your measure of similarity? What do you take into account? So if you look at all these objects here, you could actually group them into several different ways, depending upon how you are defining similarity. So again, multiple clustering results are possible based on the definition of similarity. So what are the similarity measures that are typically used in clustering, or the ones that we are familiar with? So you will find that I've listed here 3 different similarity measures or 3 metrics. And I believe we have looked at all of them before at some point or the other. So if you look at the general definition of measuring distance between between a pair of points, for example, vector x and vector y, or point x and point y, then in general, one can define that distance using Minkowski metric, where p is the parameter which tells you what value, in general, p is the parameter, and by setting p to different values, you can get different measures. For example, if you make p equal to 2, you end up with your standard Euclidean distance. If you make p equal to 1, you end up with city block distance, also known as the Manhattan distance. And if you set p equal to infinity, then you end up with a different distance. All right. So you have different values that are possible for p, and for each value, you end up with a slightly different formula for measuring the distance. All right. If you were interested to see how these different formulas or different metrics will give rise to different contours, so let's look at from the origin all the points that are at unit distance using Euclidean formula, or using p equal to 2 as the metric. All right. So in that case, basically the points are all going to lie on a circle, because points on circle are at the same distance from the origin, or from the center of the circle. However, if you were to choose a different value for p, either p equal to 1 or p equal to infinity, and you were to plot all the points that are at unit distance, then you end up with different curves. In one case, you end up with diamond, and in another case, you end up with a square. All right. So depending upon what metric you are using, you're basically looking at different contours. All right. So now let's look at what are the different clustering methods, and how can we organize them into different groups, or how can we cluster them into different clusters. One thing, there are, I think, more than thousands of papers on clustering, and if you look at all the methods, possibly there are several hundreds of clustering techniques or methods. All right, but essentially one can look at them from these two perspectives. There are methods which you can call as hierarchical methods. That is, those methods achieve clustering through different stages using some kind of tree structure. And there are methods which you can call as partitional methods, where you basically try to divide your data in one shot into different groups. All right. And when you are going through step by step or stage by stage, then you could be talking of agglomerative methods or divisive methods. That is, you could be going bottom up, or you could be going top down. So depending upon whether you have a top down method or a bottom up method, you will end up with a different clustering algorithm. So we are going to look at some of them. So as far as the hierarchical clustering methods are concerned, these methods basically build a tree type hierarchical taxonomy, and that taxonomy is known as dendrogram. And basically, if you look at this picture here, this picture is an example of a numerical taxonomy. That's in biology, that's how people use the term numerical taxonomy, and that's how they will do the grouping. So you can say, all right, we start with all the animals, and then we can group them into vertebrate and invertebrate, and then we can keep on doing further divisions. All right. And this kind of setup can be illustrated using a tree structure that has been shown here. And that tree structure is known as the dendrogram. So basically in hierarchical clustering, we will be building a dendrogram. And if you build it from the bottom up, then that's an agglomerative clustering method. And if you build it from top down, that's a divisive method. Generally, when people show the results of a clustering or hierarchical clustering using a dendrogram, basically they will be showing, along with the tree structure, a similarity scale. On that scale, you can see the numbers that tells you at what level, what was the similarity value. So if you look at this picture here, basically what this picture is showing is that you have 8 objects, x1 to x8. And pairwise, if you look at object x6 and x7, they are most similar. So that's why they have been merged first. And then when you merge a pair of objects, obviously the number of objects you are dealing with goes down by 1. All right. So you can say that now we are dealing, instead of x6 and x7 separately, we are dealing with a merged version of x6 and x7. All right. Similarly, we can see that x2 and x3 are next most similar, they get merged and so on. All right. So basically, wherever the merging is taking place, you can look at the similarity scale and say, all right, what was the level of similarity at that point of merging? All right. And you keep on merging, and basically you end up with a diagram like this. All right. As I said, we have an agglomerative method, bottom up, or divisive method, which is top down. And of course, there are direct clustering methods where you basically specify some kind of criteria, and you try to optimize that criteria. And while doing so, you end up with a result which you can call as your clustering result. All right. And most popular method for that is known as the k-means clustering method, which is the widely used clustering technique. We already mentioned how many clusters to form. Basically, other than the domain knowledge, a couple other things you can take into account. One is the cluster sizes. Should you be looking for clusters of similar size, or you allow clusters of quite different sizes? What kind of cluster profile one can generate? Do they have any meaning in terms of profiles? What is the statistical significance of differences between different clusters? And of course, if you are using agglomerative or decompositional method, then what is the pattern of merging or pattern of splitting at different stages of your process? So many of these factors are taken into account to figure out how many clusters are there. So let's look at an example of hierarchical agglomerative clustering. So basically, we need to assume some kind of similarity function so that we can measure similarity between a pair of points, or between a pair of clusters, or between a point and a cluster. All those possibilities have to be taken into account. And in this particular algorithm, we start with every object or every example forming its own cluster. So if you have 100 points to cluster, you start with 100 clusters where every cluster is just a singleton. And then you find out a particular pair over those 100 clusters that is most similar. You merge them, and basically you end up now with 99. Again, you repeat the process, you end up with 98, and keep doing till you end up at a level which tells you that, okay, that level is good enough and I needed 10 clusters and I'm at a level where I have 10 clusters. Or you can use some other method to stop or figure out how many clusters to use. All right. So that's basically a very simple method called hierarchical agglomerative clustering. The main thing here is, how do we measure similarity? Because we are not talking of measuring similarity between just 2 points. We are talking of being able to measure similarity between a point and a cluster, or between 2 clusters. All right. So you find that there are several different ways of measuring such similarity. And the 4 commonly used popular similarity measures are single link, complete link, group average, or mean. Single link basically defines a similarity using 2 most similar members. Complete link defines a similarity using 2 least similar members. Average is basically taking the average, and mean is again basically taking the means between the clusters. All right. So let's look at the corresponding formulas for these things. So these are the formulas, which are pretty standard. Let's look at these measures through a pictorial example. So let's look at the left panel, where we are using single link or single linkage as a similarity measure. So basically, if you look at these 2 groups of points, what you do is you find a pair of points such that first element in the pair is from one group and the second point is from the second group, and that pair is the most similar pair over all possible pairs that one can form. And you can say, all right, whatever is the similarity of this pair, that will be taken as the similarity of these 2 groups of points. On the other hand, if you were to use complete linkage clustering, then you will look for the most dissimilar pair and say, all right, that pair represents the similarity. If you were to use the average similarity, then what you will do is you will take all pairs and calculate for every pair the similarity, and then take the average over all those computations. And if you were to do the mean similarity, then you will calculate the mean point for first group of points, you will calculate the mean point for the second group of points, and just calculate the similarity between those 2 means and use that as your measure. All right. So these are 4 different ways in which you can define the similarity between 2 pairs of points, or between 2 pairs of clusters, or between a point and a cluster. All right. So these are the ones that are used commonly.
So for average, the average of points within one cluster?
No. You take first cluster, let's say, has 10 points, second cluster has another 15 points. So you take all pairs between those 10 and 15 points. All right. And for pairwise, you calculate the similarity and then take the average over that, and that becomes your average. Let's look at a very simple example just to give you an idea of what happens. When you want to use hierarchical clustering, the first step is, if you are given your data in the form of, for every example, you have a data vector. Then what you do is you take all those data vectors and calculate what we call as a distance matrix. For example, if you had 10 points or 10 data vectors, then what you will do is you will calculate a 10 by 10 distance matrix. All right. Now this 10 by 10 distance matrix is going to have diagonal entries all equal to 0. And of course, this matrix is going to be symmetrical. That is, the upper half is going to look like the lower half. All right. So what you do is you just take the one part of the matrix, either the upper half or the lower half. All right. So in this case, let's say that we have only 5 points, A, B, C, D, and E. And we have calculated their pairwise distances, and numbers that we get are shown here. All right. So you can see that all the diagonal elements are 0. And if I'm showing you only the lower half, because the upper half is similar to this. If you take the transpose, you will get the same. All right. So what you do is we want to, let's say, perform agglomerative hierarchical cluster. So what we'll do is we'll look at all these 5 points and identify the pair of points which are closest to each other. In terms of the matrix, we need to locate the element which has the lowest value, because if 2 points are close to each other, their distance will be small. So in this case, it looks like point A and B are closest over all possible pairs. All right. So what we'll do is we'll say, all right, we are going to merge as a first step points A and B, and we will end up with then 4 points, or 1 cluster and 3 points. All right. So once we do that, what we need to do is we need to figure out what is the distance, or what is the similarity of now point C, D, and E from this cluster that we have formed using A and B. All right. So what we can do is we can now, if we were to follow the single linkage method, then what we need to do is we need to calculate what is the distance of point C from merged cluster A and B, which is nothing but you can take the minimum of between A and C and between B and C, because that's what the single linkage does. So that gives you an answer of 3, and you repeat the same thing and you get an answer of 6 and 7 and so on. All right. So basically you form a new distance matrix. And if you look at this new set of values, you find that D and E have the smallest distance value. That means point D and E are the closest to each other, so they should be merged. So we merge them. So basically now we have to calculate what is the distance between merged cluster A and B and merged cluster D and C, or D and E, and of course what is the distance of point C from these two merged clusters. So we follow the same idea of single linkage, doing the calculations, and basically we can form the next step. So basically this is how the hierarchical clustering using agglomerative method will keep on going. All right. Now, if you want to do these calculations, there is a linkage function in SciPy, which is a package for scientific computation using Python. All right. And I think we might have mentioned it in the beginning very briefly. And this package has a function called linkage. And what one can do is one can use that linkage function to perform hierarchical cluster. All right. So that's how we can use that function. So let us say that we import NumPy, we import our matplot library, and then we import the data set and generate some random points. So as you can see here on the right hand side in the plot, what we have done is we have generated 10 points at random using sklearn library. And what we want to do is now we want to cluster these points. The color that you are seeing in the points, that color has been just added after the clustering result. All right, before you do the clustering, all the points are basically of the same color. Okay, so keep that in mind. All right, so you have these 10 points. So what we can do is we can calculate a distance matrix. All right, so again, there is a function in the Skippy library called spatial that if you import and use distance from there, you can get the distance matrix, which will be a 10 by 10. And again, we don't need the full matrix. We'll just need the lower or the upper half. All right. And once that matrix is formed, you can pass that matrix to our linkage function. All right. So you can do that from Skippy get cluster.hierarchy, import dendrogram and linkage. And basically you can say, all right, I want to do single linkage and I want to perform that on matrix that I'm designating as Y. And basically, you know, your clustering will be done. And if you want to plot the dendrogram, you can ask for that plot. And that is how the plot will look like. So if you look at this plot, basically what has happened is that it has grouped point 4 and 8 possibly as very first points. You can see wherever point 4 and 8 are there. These are points 4 and 8. So these are the points that are closest. So they have been grouped first, and then it grouped point, I think 5 and 7, which are somewhere over here, and then it grouped some other points, and it has built the dendrogram. Okay, and I did not, and I think on the left hand side you can see the similarity scale that has been shown. Okay, so basically that's how you will do the agglomerative clustering. Very simple idea. You basically pairwise merging and keep doing it till you come to a stage where you are saying, all right, I got enough clusters and I can stop. All right. Now, let's look at another example. This is of text documents. Now, if you look at the collection of text documents, these are the documents from an example that we had discussed earlier when we started talking about how to convert text documents into vectors. All right. So basically, we've taken the same example. And what we'll do is you have the text document, you generate their vector representation using the term frequency, inverse document frequency representation. And once you have the vectors for every document, you can perform the cluster. All right, so let's see. So basically, we got the TD-IDF representation, which we had done earlier. So that's just to show you again. And from that representation, we will calculate the distance matrix and then apply the clustering as we did in the previous example. So if you do that, that's how the results turn out. And you can go back and check how the different documents are being merged by looking at the text yourself and see whether it is really doing the way you expect it to do it. All right. So that's how you can actually use this method for doing clustering. Now, one needs to be aware of what kind of behavior these similarity measures are going to show. Okay. So let's look at single linkage behavior. That is, if you are using single linkage as your metric for clustering, And suppose the original set of points that you want to cluster is what is shown in the slide as original points. So you take those original points and you say you want to do single linkage clustering and you want to get two clusters, all right? Then the result that you will get is what is shown on the right hand side, all right? So you can see that basically the result is pretty good. It has nicely grouped the points into two clusters, all right? Suppose the original set of points is a little different from the previous slide, and it is what is shown in this slide, all right? That means you can see that there are two nice distribution or clouds of points, but in between there are some noisy points you can see, all right? So if you have a situation like this and you apply the single linkage behavior clustering, the end result will be what is shown on the right hand side. And obviously that's not a very good result, all right? That means single linkage behavior is quite sensitive to noise and outliers. So if you are working on a problem and you have a gut feeling that the data is noisy or there are a number of outliers in the data, and if you end up using single linkage, then chances are that your result will not be good result, all right? Because single linkage is sensitive to noise. Now let's look at the complete linkage behavior. So if you have the original points which have a lot of noisy points or outliers, and if you apply now complete linkage, the result is what you see on the right hand side, and you can say that this result is pretty decent, pretty good result, all right? That means complete linkage algorithm is less sensitive to noise and outlier, all right? However, if you have this kind of situation and you apply complete linkage, the result will be what is shown on the right side. That means complete linkage algorithm has a tendency to prefer clusters of similar size. That is, it will break large clusters. So again, if you are working on a problem where your gut feeling tells you that there are some small clusters and there are some large clusters, then you got to be careful. Now you might say, well, in 2 dimensions I can see, but what happens in higher dimension? The answer is basically you will be doing a couple of things. You will be doing the data visualization before you do clustering. So that will give you some idea of how the data is distributed. And then you will basically explore a couple of different measures to figure out what result to accept and whether you can come up with some explanation or interpretation for the results. All right. So that's really how it goes. All right. Sometimes one can introduce a clustering criterion itself in the hierarchical clustering process. So there is an algorithm which is known as the Ward's stepwise optimal hierarchical clustering. All right. The difference in this method is that what the method does is that it defines a sum of square error measure, which is really nothing but the distance of points in a cluster from their center. And you do that calculation for different clusters, add it up, and that gives you a number That's a numeric measure for defining the quality of clustering. All right. So basically, in this method, while determining the pairwise similarities of clusters, which earlier we were doing using either single linkage or complete linkage, in this case, they basically calculate the pairwise similarity by checking what will be the updated square error criterion value if I merge A and B versus if I merge B and C and so on and so on. All right. So basically you have this metric that you look at and see whether it goes up or goes down based on your supposed action. And since you want to reduce the error, so basically if it is making the error go up, you don't do that action, you do something else. All right. So that's really what this method is. Now, when you're doing hierarchical clustering, of course, other than the domain knowledge, etc., there are a couple of other things that one can take into account to figure out when to stop or how many clusters to select. One is what we call as a lifetime method. The lifetime of a cluster is defined as the absolute value of the difference between the dendrogram level at which it gets created and level at which it gets absorbed. All right. And what one can do is one can use this measure to search for clusters that have a large long time. So if you find that at some levels you have 10 clusters, but if you go below 1 or 2 levels, the number of clusters is 10 or 15 or 20. That means many clusters are getting merged very quickly. All right. So basically that's a good result. All right. That means, but if a cluster doesn't get merged for a long time, that means that's a separate cluster by itself. All right. So you take into account the idea of lifetime and figure out how you can do it. All right. The other measure that you can use is what people call as a self-similarity measure. Basically, what you do is you say, all right, here is a cluster that I have formed. Now, what is the maximum dissimilarity in this cluster? That is, locate the pair of points within that cluster that are most dissimilar. And if that value is below some acceptable value, then you say, all right, I can keep that cluster. But if that value is more than accepted value, then you say, well, I think I need to break this cluster because some of the points in this cluster are too far apart and it needs to be broken down. All right, so those are some of the things that people can use to figure out what is the right number of clusters. All right. Now, one thing very interesting about agglomerative clustering is that one can use this to perform what we call as feature aggregation, or in some sense, dimensionality reduction. You might remember we talked about feature aggregation very beginning when we were talking about data pre-processing to build a model and see whether we can merge certain features or not. All right. So basically what one can do is, since in agglomerative clustering, we use an n by n distance matrix. All right. Now, instead of using an n by n distance matrix, suppose you have d features in your data. Then what you can do is you can calculate a d by d correlation matrix. And again, this correlation matrix is going to be symmetrical about the diagonal. All right. So take this correlation matrix and apply the agglomerative clustering on this. All right. So what you will be doing is you will be merging some of the features that are highly correlated with each other. And you will be creating a new aggregated feature using those correlated features. and new aggregated feature could be simply a sum of all those features. All right. So basically, the same technique that we apply on a D by D distance matrix, you can now apply on a correlation matrix and end up with the results that basically perform what we call a feature aggregation or dimensionality reduction. So here is an example. This example uses 150 examples from IRIS data set, which has 150 examples and has 4 features. All right. So basically what we have done here is you can take those 150 examples and using those 4 features, you can construct a 4 by 4 correlation matrix. And then on that correlation matrix, you can apply your linkage function and create a dendrogram, do the merging. So as you can see here, we have done that. So the dendrogram shows merger of features 1, 2, and 3. So what we can do is we can create a new feature, which is an average of 1, 2, and 3, and keep the other feature as it is. So basically from 4 features, now you have come down to 2 features. All right. And if I was to plot those 150 points with their class labels shown as colors in this new 2-dimensional space, basically you can see the results, and you can see that with even new features, you are still able to get the classification done that you would, with the results which will be very similar to what you would have gotten if you had not performed this feature aggregation. So one can use this method not only for, of course, grouping, but also the idea of grouping can be applied to correlation matrix and then use that result as a way of doing feature reduction or feature aggregation or dimensionality reduction. Okay, we'll break here for a few minutes so that you can absorb whatever we've been talking, and then we move on to the next topic. All right, so for 5 minutes, let's have a break. All right, let's get started. Next, we are going to look at methods that we can call as direct clustering methods. And a particular method that we are going to be looking at is known as k-means clustering. This is the most popular clustering algorithm. It assumes all examples are consisting of real valued vectors. And it has a optimization criterion, which is shown here, which is nothing but the sum of squared error. And if you have k clusters, then you have k mean vectors corresponding to those clusters. And then within each cluster, you calculate how far are the points in that cluster from the mean, square up those distances, add them up, and that gives you your error. And basically what you want to do is you want to minimize this error with the idea that if the clusters or if the points in a cluster are close to each other, that means they are very similar. And also the center will be close to all those points. And the error value for that cluster will be much smaller compared to a collection of points where points are spread out very widely. In that case, the error value will be very large. So basically, this criteria prefers to build clusters that are compact and kind of spherical or elliptical in nature. And of course, this criterion works for real valued vectors. If you want to cluster examples where the values are not real valued, or some of them are real valued and some of them are categorical values, then obviously you need to make some changes to the clustering algorithm as well as to the criteria. And I leave that for you to explore in the literature to see what changes will be needed. All right. So what are the steps of performing k-means clustering? It assumes the number of clusters k is given. So we will work with a given value of k, or we will assume that, okay, that's the correct, that's the value of k. All right. With a given value of k, we can randomly initialize k cluster centers. So we can randomly say, all right, we have k clusters and these are their corresponding centers. These are picked up randomly or initialized randomly. All right. And what you do next is, then you take your examples one by one, calculate the distance of those examples from the K clusters. And if the example is closest to cluster number 1, you say, all right, this example gets assigned to cluster number 1. If the next example is closest to cluster number 5, then it gets assigned to cluster number 5. All right. So you can go over this process over all the examples. And at the end, you can update the centers of the clusters and then repeat this process and keep repeating, keep updating, keep repeating till you don't see any more change. All right. And that is when you say, all right, we can start. All right. Now, updating can be done when you have gone through all the examples, or as a given example is assigned to a new cluster, assigned to a cluster, you can at the same time do the updating for the center if you want. All right. So both ways it's possible. The idea is that you initialize centers, you assign examples, you update the centers, you repeat. All right. Now, the results can be different based on random initialization or seed selection. So if you run the algorithm different times with different initializations, you might end up with slightly different results. All right. In some cases, you might get a poor convergence or convergence to suboptimal clustering. So in general, it's a good practice to select good initialization points or good seed points. And typically what is done is that you select them using some heuristics or use some other method to get the initial values and then run the k-means from that point onwards. So if you look at this slide, on the top, I'm showing you the original set of points. All right. So basically, let us say that is the ground truth. That's how we have 3 clusters. All right. A green cluster, blue cluster, and red cluster. All right. If I form 3 clusters out of these points and look for the criteria that is minimized, then basically I get the result which you can call as the optimal clustering result. That's where the sum of squared error is minimum. All right. If you end up with a slightly different result that is shown on the right hand side, that you can call as a suboptimal result, because the criterion value in this case will be slightly more than the optimal value. And chances are, depending on the initialization, you might end up in the suboptimal result, or you might end up in the optimal result. Although in this case, the difference is very minimal, but it's possible. This slide just shows you what happens at different iterations as you go through. So if you look at iteration 1, the 3 points marked with the crosshair, those have been selected as initial points. Let us say randomly, you just pick them as initial points. All right. So what you do is you take those initial points and you assign all the points to one of these 3 initial centers. All right. And when you do that, basically that is what you get at iteration number 2. All right. So if you were to plot the results of iteration number 2, that is what has been shown. All right. So with that, you update the center. So centers now you can see have moved a little bit. And now you run the algorithm again, and you end up with iteration 3. Again, there is some change in the assignment. And if you continue, again, you get updated centers, you get iteration 4, iteration 5, iteration 6. All right, so somewhere at iteration 6, you can see that if you were to run it again, no change will take place. So that's when you say, all right, my algorithm has converged, my procedure has converged, and that's the result we get. All right. So that's simply k-means clustering, pretty simple algorithm. This slide shows you the results with different seed points. All right. So you will get slightly different result, but the process will be similar. Now, if you want to look at an Excel implementation in Excel and read a little bit more, you can take a look at this blog post. Now, how do we evaluate the clustering results? All right. Obviously, we are using the sum of a square error as the criterion. So if you have two clustering results, you will choose the one for which the error is smaller. All right. Only thing you have to remember is that if I keep on increasing the number of the value of k, the error will keep going down. All right. So when you are comparing this criterion value, you must compare it for same value of k, because if one has a slightly different value of k, then the comparison doesn't really make sense. All right. Now let's look at an illustration of k-means. So basically, the data set that we are going to be using for this illustration is known as the US arrest data set. This data set has arrest information for 50 states. And the information is basically in the form of a rate of arrests for three types of crimes per 100,000 residents. And the other attribute is urban population percentage. So basically you have 4 features that are shown here, all right? And you can see the numbers here, and you can see that there are some numbers that are negative. You might wonder why the how arrest rate could be negative. The reason is that the data I'm showing you is the data that has been normalized. So if you normalize the data, basically you are trying to get for every feature 0 mean. So some values are definitely going to be negative. All right. So basically what we have done here is we've taken the data and the data has been normalized. And once the data is normalized, we can apply the k-means clustering. And you can use the sklearn basically and do the clustering. And we will show you the results using unnormalized as well as with normalized. All right. Now, typically what you do, since you do not know what is the number of clusters, so what you will do is you will run the clustering algorithm for different values of k. In this case, we have run the algorithm for values of k ranging from 2 to 9. Obviously, as we keep increasing the value of k, our error will go down. All right. So the shape of the curve is known, it's going to go down. All right. But if you look at this curve, there is at k equal to 3, you can say there is a knee point. That is, after that point, the rate of error going down is little less than the rate of error going down prior to that point. So that knee point kind of represents the correct value for k. So in this case, you will select, if you were to look at this without anything else, you'll say, all right, I'm going to take k equal to 3 as my result. All right, and then you will form you look at the 3 clusters. All right. Let's do the same thing with normalization. So with normalization, this is the plot that you get. All right. So what has happened is, if you now look at this plot, the knee point now is shifted. Now k equal to 4 is the knee point. All right. Again, the reason for normalization is similar to what we have been talking earlier. That is, different features might have different scales. So what you want to do is you want to get everything in the same scale. All right. So normalization is preferred. So we will accept k equal to 4 as the result. All right. Now, once you have k equal to 4, you can go to different clusters and find out what are the members in those clusters. So if you look at cluster labels for the first 5 states, Alabama, Alaska, Arizona, Arkansas, and California, you will find that Alabama and Arkansas are in the same cluster. Arizona and California are together in another cluster along with Alaska. Okay, that means you have 2 clusters, Alabama and okay, what Arkansas. All right. So basically, you can say that those 2 states are pretty similar. So it makes sense that they are in the same cluster. And California and Arizona are again very close, pretty similar. So again, makes sense that they are in the same cluster. All right. And Alaska might be there because it's showing results that are similar to them. All right. So one can have that kind of interpretation and say, all right, this is what's going on. And that's how we are getting these results. All right. So that's how actually k-means works. All right. Now, as I said, the main issue with k-means is selection of seed points. For small problems, you can actually run this with multiple seed points. This is what a sklearn will do for a small problem. All right. For some of the bigger problems, what you can do is you can combine hierarchical clustering with k-means. So what you do is you take, suppose you have very large number of examples, all right? So what you do is you sample those examples and select a smaller sample set out of those examples, all right? Typically people use, if n is the number of examples, then you take a square root of n and say, I'm going to sample that many examples from that set. And then using that set, you apply the hierarchical clustering. And if you want k equal to 5, then you apply that clustering to get to the level 5. All right. So at level 5, then you have the clusters, you take their centers and use those center values in your k-means algorithm as the initial points, and then run your algorithm on the entire data set. So that's typically what people will do to figure out what should be the good choice for initial points. All right. And if you have especially a very large data set, you don't want to go over that data set again and again. So typically what you can do is, again, you can take different samples of that data set. And for each sample, you calculate the k-means. And then when you look at the next sample, you update the means and so on and so forth. So there are a number of variations. As I said, people can come up with their own variations. So basically, that's how this gets done. All right. So just mention, all right. So basically, you can do that. There is another algorithm which is known as the mini batch k-means clustering for large data sets. So choose a random sample of data, perform k-means, save the k-means, choose an, yeah, this is what actually I mentioned earlier. So that's the mini batch algorithm. All right. So this shows you the results that you will get by looking at all the data points or by doing clustering using mini batches. And you can see that the difference is really very minuscule between the 2 results. And the advantage you get with mini batches that it saves you time, as well as you don't need to store everything in the memory. Okay. All right. Another quick thing is indirect clustering through iterative optimization. This is the same idea that is used in the Ward's clustering. So suppose you already have a clustering result through some method. And what you want to do is you want to see whether I can refine this result a little bit or not. So one way of refining is to say, all right, what will happen to my result if I took this point from cluster A and moved it to cluster B? So when you take a point from cluster A, the square error for cluster A will go down because you're removing one point. All right. When you move it to B, the square error for B will go up a little bit because you're adding a point there. That point is going to contribute to the error. All right. So as long as the error that goes up is less than the amount of error that goes down, you have a profitable trade. You want to trade. All right. So that trade looks good. On the other hand, if the error that is going up is, and the error that is going down, so error going down is less than the error that is going up. That means overall error is going to go up. So that's not a good trade. So one can define whether a trade is good or bad by comparing these two quantities. What will happen to the error contribution from cluster A and what will happen to the error contribution from cluster B if I was to move point from cluster A to cluster B. All right. So one can explore this possibility, and by looking at the math, one can actually write down a formula which is shown at the bottom, which tells you whether a particular trade is profitable or not. All right. So what one can do is one can use this kind of fine tuning sometimes to adjust your results to see if any improvement can be done or not. All right. So these are the steps which I just mentioned. All right, let's talk about cluster validity. Again, how do we validate our clustering results? One possible approach is to run the algorithm with different parameter settings and see how things change. So if the change is not much, that means your results are pretty robust, pretty good. All right. You can also check whether the clusters are compact or not. Another point which I mentioned right in the beginning, test them against an hypothesis or domain knowledge and see whether you can explain the results. All right. In many cases, one can use the ground truth. Of course, if you have the ground truth, you don't need to perform clustering because you already have the result. The situation where one would use this is where you want to come up with your own clustering algorithm. So typically, if you are coming up with a new algorithm or you are designing your own version of something, what you like to do is you like to test it on something for which the results are already available. So if you want to create a new clustering algorithm, or if you want to make some changes to an existing algorithm, obviously you'll make the changes, but how do you test it? So you will test it with a data set for which the clustering results are known. The ground truth is known. So in certain situations, ground truth is available. Those are the situations where you are coming up with your own ideas or own techniques. All right. So in those cases, one can actually, again, check the results against the ground truth and see whether your results are good enough or not, or whether your method is doing good or not. All right. So there are one or two ways of defining these goodness of clusters or validity of clusters. One is what is known as the Silhouette coefficient, which basically computes these two quantities A and B as shown here. And then calculates a single, for a single sample, calculates the coefficient S and then adds them up for all the points in a given cluster, and that gives you the Silhouette score. All right. So one can look at those scores and see whether those scores make sense or not. Another one is the idea of using a RAND index. All right. In RAND index, the basic idea is that suppose you have n examples and you want to pair them. So basically, if you have n examples, you want to pair them, so you can have n times n minus 1 by 2 pairs. All right. So you form those pairs. And then you see in your clustering results how many of those pairs are present, how many are absent, and so on. So you have a set of pairs from your ground truth. You are looking at pairs that are formed by your clustering process. So what you can do is you can compare these two sets of pairs and see whether, and you can calculate an index value, which is very similar to the Jaccard coefficient that we discussed earlier, and use that value as a measure of your cluster validity. All right. And here is an example that I leave it to you to read. And in fact, you can read much more details on clustering results by going to this blog post. So I suggest that you do that. And what I'll do is I will stop here, and next class very quickly we will take care of multi-dimensional scaling, all right, which is nothing but another way of doing data visualization. Okay.
Professor?
Or why not we finish it? Give me a few minutes, all right? We can start a new topic next time. All right, so let's look at multi-dimensional scaling. As I said, it's another way of doing dimensionality reduction or plotting the data and looking at it in a two-dimensional space. All right. Of course, what I'm showing you in this slide is multi-dimensional scaling applied to different automobiles manufactured by different manufacturers. And of course, each automobile is being characterized by certain attributes, or people have been asked through surveys different questions and rate these automobiles on different attributes, and using that result, this is what you are able to do. All right. So multi-dimensional scaling is very similar to some of the techniques we discussed earlier for mapping the data from a high dimensional space to a low dimensional. All right. So in this case, again, we map the data to a 2 or 3 dimensional space. All right. This technique became very popular because it is supposed to uncover hidden relationships that are present in the data. And this technique is mostly used for marketing or business purposes. And basically, you know, you're all familiar with, you've seen the ads of, you know, Coke test or, you know, blind test of Pepsi or Coke or soda and this and that. All right. So marketing people are always running surveys and, you know, tests and things like that. So how do they compile those results and how do they present them in a two-dimensional chart or fashion? All right. So that is what the MDS does. And basically it's supposed to capture what we call a perceived similarity. And it is also known as perceptual mapping. So if you were to apply this for soda, this is how, based on lots of surveys of people, this is how, you know, different sort of flavors kind of map into a two-dimensional space. And similarly for automobiles, this is kind of results one will get. What is being done mathematically is very similar to what we talked about in the TSNE method. You define the distance or similarity in the higher dimensional space. Through some mapping, you define the similarity in a lower dimensional space and define a criteria that captures that. And what you want to do is you want to manipulate that mapping so that this criterion is maximized or minimized. All right. So that's really what multidimensional mapping is. And this criteria is typically known as the stress. And there are a number of different criterion that people have used and defined. The basic distinction is a metric criterion and a non-metric criterion. That is, in a metric criterion, that's one we are looking at the distances. In a non-metric criterion, you look at the ranking. So if item A and B, if B was the nearest item to nearest point to item to point A in the original space, in the mapping, do we still get B as the nearest point or not? So instead of looking the actual distances, you look into the ranking of neighbors, and basically the criterion is based on that. All right. So you have metric MDS and non-metric MDS. All right. And I'll just show you one example here, and you can basically do this in sklearn library. So we'll use the same data that we used earlier for the states, 50 states. So if we apply the multi-dimensional scaling and map the results into 2 dimensions, basically you end up with 3 groupings. So you can say, all right, there are 3 clusters in that data, which we found if we were using the data for clustering without normal. All right. Now, if you look at the groupings, you can see that again, some of these groupings make sense based on how the states are grouped together. All right. Similar to what we had seen earlier. All right. So basically, one can use MDS along with clustering to figure out what might be the best number of clusters or what might be the best value for K. So that's why I wanted to mention this. All right. So let's just summarize clustering. Clustering has numerous applications across many disciplines. Many clustering algorithms are there. Getting the right number of clusters and validating clusters in absence of any ground truth is a tough thing without domain knowledge. And MDS is a good visualization tool that can be used for explaining how similarities are perceived and get a good idea of the number of clusters. All right.